This video looks at system stability with an observer, or the separation principle. So the previous video demonstrated that you could derive an observer gain L to give the desired state estimation error dynamics. So if we have a system x dot equals ax plus bu, and an observer given with the same A and B and C matrices, but with the additional term here of a matrix L times the error between the observer output and the system output. And what we showed is that that gives error dynamics with a transition matrix of A minus LC. And obviously L is a parameter we can choose. So in practice, an observer gives state estimates, that's Z, which are going to be used by state feedback for system control. So there's going to be an interlinking here, or a coupling. And what we want to know is what is the impact on overall stability. So if we combine an observer, a state feedback and system dynamics, we're going to end up with a large number of parallel models. So here's the underlying system, x dot equals ax plus bu, y equals cx. Here is the observer, and in addition we've now got a state feedback, but critically this state feedback uses z, but the u goes into the original dynamics. So what we want to know is this overall system of equations closed loop stable? For now, we're going to assume no parameter uncertainty, so we'll assume that A, B and C are known exactly. The easiest way to analyze these coupled dynamic equations is to construct a single equivalent state space model with states x and z. So here we go. You'll notice that the top is the system. You see we've got x dot equals ax plus bu, u equals minus kz, and y equals cx. And underneath that, these equations represent the observer dynamics. If we combine these into a single model with states x and z, this is what we get. You'll see the top row gives you x dot equals ax minus bkz. And the bottom row gives you z dot equals lcx, and then a minus bk minus lc times z. So we have basically a larger state space and a larger transition matrix. And so this governs, basically this tells me about my closed loop dynamics, and it has both x and c in it. And we want to know, is this transformation matrix going to give me stable dynamics? So what we're going to do is use a similarity transform to expose the underlying modes or behaviors. So let's first of all repeat what we've got here, and now let's propose a similarity transform. So here it is. I'm going to use t is given by I0, I minus I, and you'll see t inverse comes out to be the same. So if I pre and post multiply by t and t inverse on this transformation matrix, this is what I get. And you'll remember from the earlier sections that the eigenvalues of a matrix which has gone through the similarity transform must be the same. So therefore the eigenvalues of this new matrix are the same as the eigenvalues of the original matrix. But the nice thing now is I've got this 0 on the lower diagonal. So because of that, I can state by inspection that the eigenvalues of AC are given by the eigenvalues of this block and the eigenvalues of this block. And I can do that because I've got this 0 down here. So what do you notice? The closed loop eigenvalues come from the eigenvalues of A plus B minus BK and the eigenvalues of A minus LC. So the closed loop poles, when combining state feedback with an observer, are the poles you get from the state feedback design and the poles you get from the observer design. And that's why people tend to use this word, the separation principle. You can do the two designs separately and you retain the properties of both. So we can design the state feedback and observers independently one of another without any impact on overall closed loop stability. We have, of course, assumed that there is no parameter uncertainty, and we've not considered the impact of the combined design on behaviour. We've said where are the poles, but there's more to behaviour than just the pole positions. So let's do some MATLAB illustrations. We're going to compare performance with an observer and assuming the states are measurable. So we're assuming, basically here, we're assuming that x is known, so we don't have to estimate it. We want to know how the overall behaviour changes with different choices of observer poles, because you can choose them. Do you want the observer poles to be fast or slow? And we're not going to consider parameter uncertainty. So here's the first example. Now there's 5 lines here, so we'll go through them slowly. First of all, the red line is the error with the observer. So what we're talking about there is this y minus ym. How quickly does the observer output converge to give the correct output? The blue y is the output from the observer with, now I should explain here, basically you've got control with observer, that's one option, and the second option is control with u equals minus kx. So they're entirely independent simulations. So if you're doing control with u equals minus kx, there is no observer. So this green plot here, there is no observer. So that's what you would get if you just knew the states, if you could measure them precisely. And you can see that green line is quite nice, and the blue line for the corresponding input. So these two go together. So that's what would happen if you had no observer and you could just measure the states. But what happens when you can't measure the states and you have to use an observer? You get this pink and this blue line. And the notable thing, look at this pink line. Look at that input. And the blue line, the behaviour is poor. And why is the behaviour poor? Because during transients you are using u equals minus kz, and z is not equal to x. So as soon as you include an observer, you're basing your control decisions on the observer state, but if the observer state doesn't match the system state, then of course your control law is going to lead you astray until the errors between z and x converge. And that's what you see here. During transients, behaviour is not very good. And here, we should summarise, I've made the observer poles 10 times faster than the system poles. So I've said I want this error to converge very quickly, but look, I've paid for that with some horrible transients. Okay, so what happens if we say, well, let's be less ambitious. Let the observer poles only be twice as fast as the underlying dynamics. And what do you notice now? Well, I've still got fairly nasty transients, but not as bad as before. So by being less ambitious with my observer poles, by accepting that the error is going to converge a bit more slowly, actually I've handled the transients slightly better. So although the input's still large, it's not as large, and the error convergence is still reasonable. What happens then if I make the observer poles slower than the system poles? Well, here we have a different problem. Now you look at the error, and the error is too slow to converge. So z tends to x, too slow. And as a consequence, you get poor behaviour, but for the opposite reason. So conclusion, we've introduced the separation principle used for analysing system stability with state feedback and a state observer. And we've shown that you can independently design the state feedback and the observer gain to give the specified poles, so we can assess the overall closed loop stability, critically in the absence of parameter uncertainty. However, here's the key point, stability and performance are different things. So the separation principle will guarantee stability, but it will not guarantee performance. And the impact of observer pole selection on overall closed loop behaviour, if I write here, is not obvious. It's not immediately obvious how you go about designing these observer polls in order to have the least possible impact on closed-loop behaviour. Consideration of these issues, however, is beyond the immediate remit of this video series, and you're likely to want to look at things such as a Kalman filter.